This is a paper review for AICE Marine Science, paper 11 from the May-June 2024 series. These exams are public and you can Google search for this and print yourself out a copy. You're more than welcome to follow this along with the mark scheme and see how it's implemented. Things you're going to need for this exam. It's a decent one. Okay. We're going to need pens, ballpoint pens. Highlighters are always good. You can highlight questions, you can highlight parts of a graph. The only things you cannot highlight are your own work or anything you're providing for Cambridge to mark. Always have a calculator. And though on this test it's really not going to be necessary, we should always have a really good pencil with an even better eraser. That will be definitely prevalent on exam 2, paper 2. And a ruler if needed. Hopefully that's something that your schools will provide for you. There we go. All right. You'll have an hour and 45 minutes long to take this. That makes every mark worth about a minute and 20 minutes. As stated on the front, answer every question. Use a black or dark blue pen. No need to use any erasable pens or gel pen. Gel pens can bleed. Erasable pens work based on friction and heat. And by the time your tests get to England, they could be blank. Diagrams and graphs will use a pencil. Your name, your center number, candidate number will be in the boxes at the top of the page. Write your answer to each question in the space provided. And with that, if you run out of space, you need to continue it. You can always answer the question that you haven't been able to finish in any of the blank spaces provided throughout your exam. And you would just indicate exactly what question you were answering in that area. Do not use erasable pen or correctional fluid, so no whiteout. You can always cross things out. Do not write in the barcodes like right here. We wouldn't want to do that. You may use a calculator. Show all your work and use appropriate units. So they're telling you to use units and still you might forget. Make sure you show all your work, especially if they ask you to do it, then you are expected to do it. Otherwise, it's just good practice to do it. All right, starting off, I recommend, I'm going to start from the beginning, but when you are taking your exam, I do recommend starting in the back section where you have the extended responses. Those are going to be more time consuming and just take a lot more of, I think, like your academic energy. All right, this is a new type of question. We haven't seen one like this before. Love it. We see an atom of calcium. It is an atom. It's not an ion yet. It has not given or taken any electrons. Okay, that's a good thickness. We need to name the particles found in the nucleus and the charges of each particle. Name particle in the nucleus and the charges. 2 marks. Mark for each column. Name of the particle. It doesn't matter your order. Say proton, and it's positive. And also we have neutrons. And those are neutral. All right, that's a pretty quick one, and that honestly shouldn't be taking you 2 marks worth of time. Would be about 2 minutes and 40 seconds to do. All right, also from the beginning of the syllabus in Unit 1, looking at the salts that are abundant in the ocean. Marine organisms use dissolved calcium salts for production of bones and shells. State the name and the formula of one calcium salt commonly used by marine organisms. And in order to get all 1 mark for this, we need to be correct on both parts. And the salt we should be thinking about is going to be calcium carbonate. Its formula is Ca and carbonate is CO3. All right, and I'll mention I write uppercase and lowercase for no reason at all. That's it. There's no reason. The other salts that we need to know that are abundant in the ocean is sodium chloride and magnesium sulfate. Sodium chloride and calcium carbonate, we also need to know based off what they look like. Calcium carbonate forms that lattice structure. Okay, and then, it gets like 3D. Has some depth to it. And calcium carbonate looks like this. Here's our calcium. Here's carbonate. C, 1, 2, 3. And if I'm drawing it a little bit incorrect, that's because I'm not a chemist. Magnesium sulfate, per the syllabus, you do not have to know what that looks like. For good practice, I have my students identify it. That looks actually a lot like calcium carbonate, but there's just one more oxygen. So that would be magnesium, and then your SO4. You would have 4 oxygens stemming off of it. Okay. Explain the role of hydrogen bonding as sodium chloride dissolves in water. 4 marks. This is also something that you can draw. You can definitely draw this out as long as you're labeling your molecules, maybe labeling any processes that's happening. You can get marks for this too. So we need to first consider command words. Explain, which is why or how or give reasons for, so you know to the depth of the level of answer you need to give. So hydrogen bonding. Hydrogen bonds form between 2 different water molecules because of those partially charged atoms. The opposite partially charged atoms are attracted to each other through electrostatic forces. And it's going to be those same partial charges that are going to be attracted to sodium chloride's charges. So what this will end up looking like, and as I draw it, I'll also write out the answer. Water. Zoom in here. All right, so our oxygen atom. It has 6 valence electrons, and it needs 2 more to have a full outer shell. I'm drawing it like this on purpose. And then we have 2 hydrogen atoms. Our hydrogen atoms each have 1 valence electron, and they require 1 more to have a full outer shell because hydrogen only has that first shell or the first orbital, and it can only hold 2 electrons max. Oxygen's outer shell can hold up to 8. Okay, and so the ones hydrogen's going to have, here will be hydrogens in the darker red. So now if we're looking at it, hydrogen will be able to have these 2 electrons and its outer shell will now be full. This hydrogen has these 2 electrons and its outer shell will be full. And then in total, the oxygen is able to, blessed day, my gosh. All right, The oxygen is able to have 1, 2, 3, 4, 5, 6, 7, and 8 electrons in its outer shell, and now it is full. And because of this, oxygen is able to hold more electrons. That makes it partially negative, and your hydrogens alternatively would be partially positive, just because they're not full negative, they're not full positive charges. They're sharing electrons. This is a covalent bond that forms water. Covalent forms water, but a hydrogen bond bonds one water molecule to another water molecule. And so when they bond, it would look something like this, perhaps. That would be your hydrogen bond right here. Because the oxygen is partially negative and your hydrogen is partially positive. And so those opposite charges are attracted to each other. And that's caused by electrostatic forces. This is the same reason why your water molecule is going to be attracted to sodium chloride. So if I am just going to draw, I'll draw one chloride ion. Notice the name change, it's an ion. Chloride is not chlorine. Chloride now has a charge on it because it's going to be taking an electron from sodium. Great, that's perfect right there. Okay. Here's chloride. And then the partially positive hydrogen atoms will be attracted to it. So here's one. Oxygen, hydrogen, hydrogen. All right, and if we wanted to get marks just for sketching this out down here, if you want marks for that right there, then we need to complete our drawing. And so we need to show the charges on them. Oxygen is partially negative. Notice this is not the part that is attracted to the chloride ion. It's the partially positive hydrogens. Now this would be happening to the entire lattice structure. There's Na, here's Cl, here's Na, here's Cl, Na, Cl, Na, Cl. And likewise, sodium chloride will form a crystal structure because of its opposite charges. And opposite charges attract. So if I were to draw this same structure for sodium, it would have Na plus in the center, and the water molecules that would be attracted to it, they'd be attracted to it off the partially negative oxygen atom side. Okay, and we're ready to answer this now. We need to introduce water. Water is polar, or we could describe it. And if you're not sure that you could also describe it, then maybe you would want to put both. The hydrogen atom, it's still an atom. It never becomes an ion because it doesn't give or take electrons. It's just sharing, but it just doesn't share equally. The oxygen atom is partially positive. Did I say oxygen? Sorry, the hydrogen atom is partially positive, and the oxygen atom is partially negative. Now, it's not like you know the mark scheme going into this, so I would consider this command word explain and go a little bit further. I would say why it has those charges, though it is not partial charges. It is not on the mark scheme, but for good practice, I'll put it because you don't know what's going to be included on the mark scheme, and if we're answering the command to explain, then that's what I'll do. The oxygen atom attracts more electrons. And you can abbreviate electrons E with a minus. That's not an abbreviation that I'm making up. That is real. Okay. And so obviously then we could also say the reverse argument. If that's the case, the hydrogen atom does not attract as many electrons. Now we need to introduce sodium chloride, and then after that we can talk about the attraction, and ultimately that is going to cause some dissolution. The chloride ion, could also just write this out as chloride, not chlorine, it's chloride because that's a charge. Has a negative charge. Because it takes an electron from the sodium ion. We'll call sodium an ion because we've just said that it's lost an electron. And when we give and take or gain or lose electrons, that's what's going to cause it to be called an ion. Of course, you could say the reverse argument and you could introduce sodium first. It's fine. And you could talk about sodium being positive and chloride being the one that's taking an electron, causing sodium to be positive. All right, and then we talk about the attraction. It doesn't matter if you talk about the partially negative oxygen atom or the partially positive hydrogen atom. Partially positive hydrogen atom is attracted to the chloride, negative chloride ion. And again, following the command word, and just, what I've seen throughout other previous paper ones, this would be a time where you could talk about why and like the opposite charges being attracted to each other. And so if I'm, again, following this command word explain, I'll add it, although it is not on the mark scheme. But again, we don't know what's going to be at the mark scheme or not. And I should also mention, for anybody who's not my student, I have just always written marks with bullet points. So I bullet point what the next mark is going to be so that it's obvious. I often get asked, can we use bullet points on the exam? You can, but you have to be explicit in what your statement is relating to. So where you have this explain question, you need to kind of give explanatory responses with it. For example, like this causes, or this is due to. This will make dissolved oxygen decrease. This will cause productivity to increase, things like that. But the bullets do help with you trying to make sure you're hitting the amount of marks that this is worth. Okay, so just for good practice, I'm going to put due to opposite charges attracting or this is caused by electrostatic forces. Finally, the last mark that is published is that this this attraction that we drew here, this would be almost like the hydrogen, partially positive hydrogen atoms, like attacking those chloride ions. They're not an attack, it is an attraction, but it is similar to that. And likewise, the partially negative oxygen atom would be doing the same thing to the sodium, and this is what's going to be breaking them apart. This separates the lattice structure. You could say this separates the sodium and the chloride ions. But that will be it for this question, and then we move on. Oh, great. The density of water is going to change as it freezes. Explain the changes that occur as water freezes, and then use the kinetic particle theory in your answer. Okay, so we need to consider density of water and freezing. Command word is explain. Changes that occur as water freezes. We're going to be talking about the changes like within density, but also why. We need to say why is explain. And then they tell us to include kinetical particle theory in your answer. Okay, density is mass over volume. And we know that when water is frozen, it is less dense than the liquid form. And it floats. Explain means why or how or give reasons for. As the water freezes, so what's happening is the water is starting to get cold, 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 and then it hit freezing. And then we need to include the kinetic particle theory in your answer. So essentially, we need to talk about kinetic energy. All right, and if you haven't seen any of my abbreviations before, just something I've always taken back with me from college, NRG, instead of saying energy, I put NRG. Do not do that on your test. That is not like a real science abbreviation. Just for the sake of practice, that just saves my hand from writing all these letters. Okay. And in brief, kinetic particle theory or kinetic energy, as the temperature goes down, that means that kinetic energy is also going down. And the particles are going to move slower. If it's water, they're not going to slide past each other at the same rate. And as it turns towards a solid, they're going to vibrate in place. Okay, and so I need to talk about as water cools. And this is where I'm going to introduce the kinetic particle theory. The kinetic energy decreases. We could also reference its movement. Water molecules move slower. You can put H2O, that's fine, because that's nothing I made up, that's real. I use a lot of arrows. Don't use arrows on your exam because it's meant for interpretation. So the kinetic energy goes down, kinetic energy decreases, kinetic energy down. Like it's not explicit enough. Don't use arrows. Not for your actual exam. Okay, and so why is this happening? In solid water, our hydrogen bonds start to reform. Hydrogen bonds are weak. and they're easily broken with maybe a little bit of heat, so a little bit of kinetic energy, some movement in the water, but they do also reform easily, especially if they're in their liquid form. But here would be an example of their solid form. And so this also will form like a crystal-like structure. And what they're reforming is what we also talked about right here, the hydrogen bonds. Hydrogen bond, hydrogen bond, hydrogen bond. And so this is why if you put something that has a lot of water in it and it's in its liquid form, you put it in the freezer and it does freeze, that liquid can actually like explode in the freezer. And it's because when water freezes, the hydrogen bonds are reforming and you cannot fit the same amount of water molecules within that same volume, or essentially in that same space. And if we look back, density is mass over volume. Within the same volume, right? Volume isn't changing. I cannot fit the same amount of mass in there. So the mass is going to end up being less. And if mass is less, it's literally like the weight of the water, the mass of the water, then we're going to, like, we have less water molecules in there. It's going to not have the same mass, not have the same weight when it's frozen. And that is going to make it essentially lighter or less dense, and it will float on top of its liquid form. Liquid water is very, very compact with water molecules right up next to each other. All right. The slower movement allows hydrogen bonds to reform. I'll be a little bit more explicit, between the water molecules. Okay, and I'm going to talk about them being more spread apart, because ultimately I need to get this answer to end up talking about the fact that they're more spread apart because the hydrogen bonds reforming. We're not going to have the same mass, the same amount of water molecules in there. And that's going to cause it comparatively, if you're comparing it to its liquid form, it's going to cause the frozen form or ice to be less dense and it will float. And finally, this causes ice to be less dense. I'll put in parentheses, why, due to less. I'm putting in parentheses because it's not actually on the mark scheme. I don't know why it's not. Again, you're not going to know if it's on a mark scheme or not. If you know that this is still applicable to your command word and the question that you're answering, then include it. The worst thing that could happen is they are like, well, we didn't, that wasn't a mark that we were including, or maybe you write something that's irrelevant. As long as you don't contradict yourself and you say something like, this causes ice to be less dense due to more water molecules per volume, As long as you're not contradicting yourself and saying something that now is going to be wrong, then you won't lose any marks. The only way you can lose a mark is if you immediately contradict yourself in the same answer. So like, as water cools, kinetic energy goes down, but then somewhere you say, as water cools, the kinetic energy is going to increase. Well, you're going to lose the mark for saying kinetic energy decreases, because do you really know what you're talking about at that point? If you're saying both things are happening, so that is a contradiction, and that is really the only time you're going to lose marks. Due to less water molecules present in the same volume. Again, why things explode in the freezer. You're not changing the volume of like the container or the vessel that the liquid's in, and solid water can't fit in there. Final mark, I'm going to squeeze it in. Well, it's not the final mark. This is the final mark, but the last statement is that it's less dense, and so it's going to float. Okay, so we talked about water cool. Dang it. There we go. We talked about water cooling, right? And they said as water cools, we talked about the kinetic energy going down. They mentioned can include kinetic energy. The lower kinetic energy, or the slower movement, allows hydrogen bonds to reform. The reforming will cause water molecules to be more spread apart. So all of this is like explain the changes. And what that change is going to do is going to affect the density of water. This will cause ice to be less dense, and it will float. And this is a good example of where I just previously mentioned about using bullets. You could use bullets, but I use the bullets in a way where I was also explaining and following the command word of how I need to answer this, right? So leading off from that first statement, water molecules move slower, I elaborate. The slower movement allows hydrogen bonds reform. Next mark. This reforming, this causes, so that is an explicit way to still use bullets and still answer the question correctly. All right, and this one we have to do some metric conversion. Calculate, that's our command word, the volume of a mass of water, and they give us our mass, that has a density of 1,022 kilograms per cubic meter, and they give us the density. Show your work. You definitely are going to get a mark for showing your work, and it's 2 marks, so you got to do it. And they already give us the unit, but the unit is meters cubed, so that's the volume. And they told us to calculate the volume. All right. If you know triangle math, it's my favorite math. Start with what you know, and then you can figure out how to solve for volume after. We know density is mass over volume. And so if I'm solving for volume, I'm going to do mass over density. Okay, and my mass, 14,863 grams, and my density is 1,022 kilograms per cubic meter. And you can put kilograms per cubic meter like that. Cambridge likes to take it out of the denominator and do its reciprocal, which is why you see the negative exponent. And if you don't math that way, that's okay. I like to write it like this with the division sign there so that I actually know what units I'm dividing by each other. It's fine to write it either way. We have a problem though. The problem is we have grams and kilograms. Wah, wah. This was a particular skill that students weren't so great at, so I would expect it to come back again. I can't recall what test it was. I think it was October, November 2024. There was a question about calculating the depth of the mantle. They gave like a slice of the earth, and then they wanted you to calculate the depth of the mantle. But they were in, it was in scientific notation, and the scientific notation had different exponents with it. So I'm sure, adding and subtracting in scientific notation is probably something we need to brush up on. Where's the lock screen? Oh, there we are. All right. And this too, like some relatively simple math, something we might need to brush up on. So this is the King Henry in chocolate milk. That's usually how a lot of us remember it in the States. King Henry died by, that's your base unit, drinking chocolate milk. A lot of king deaths we're going to have to remember. It doesn't matter. If you want to go from the kilogram to the gram, that's fine. If you want to go gram to kilogram, that's also fine. We just need to have the same units. And if you want to divide and then do this at the end, that's fine. As long as you get the right answer. I'm going to start at my base unit with this gram. I'm going to change the 14,863 to kilograms. And so I'm going to go 1, 2, 3 decimal points over this direction, so towards the left. And so my 14,863 here's my decimal point. I go 1, 2, 3 to the left. So now it's going to be 14.863 kilograms instead of grams. That's a disgusting arrow. Okay, I can live with that. And now we can actually divide. And what you should see is your kilograms are going to cancel, which is great because we're left with meters cubed, and that's what our answer needs to be in. And when you divide this, you're going to get 0.01454. They don't tell you how many significant figures to give. So we can leave it at that. Okay, 12 marks down. All right, we're out of the water chemistry, thank goodness. Okay. Always read what's at the top, you guys. Always read what's at the top. It's not just an instruction. There's a lot of times that there's little information there that you're going to need. So we see an ascidian, which is also a sea squirt, and a reef shark. Both organisms are in phylum Chordata. Ooh, you know what they're going to ask. State 2 features both organisms have in common during their early development. And this is in that massive unit 4.2 with the classification of marine organisms. And it's kind of mixed in with the bony fish and the cartilaginous fish. Despite seeing the ascidian and thinking there's no way that you are also in the same phylum as a human, and it's a sea squirt and a shark and mammals, it's whatever. It is what it is. It's sometime in development, they're going to have 4 common things. They asked state 2, so you have to give 2. If you give 3, it doesn't matter. If you give 2 and they're wrong, and then you put a third answer down here and it's correct, nobody cares. It is still wrong. If you do a correct answer on 1, a wrong answer on 2, and a correct answer on 3, only 1 and 2 are being read. If you give a correct answer on line number 1, you put a comma, and then you give another answer on line number 1, and it's wrong. And then you give an answer on line number 2, and we'll say this one is correct. Guess what? They read their answers just like we read in English. We go up and down, and then we'll left to right, and then up to down. So this would be answer 1. This would be answer 2. What you put on line number 2 doesn't even matter. You already gave your 2 answers, and that's what they're going to be marking. And this makes sense, and this is so, candidates can't just do like a Hail Mary and just put whatever words they think will work. All right, you can have the post-anal tail, a notochord, chord. I did this last month too. Bless my own heart. A dorsal neural tube. And the last one, like where our pharynx would be, they look like gill slits, they are not gill slits. This is called pharyngeal slits. If your teacher has not explicitly told you for sure to know these, the max I've seen them ask is for 2. Know these. If you don't have it on paper 1, I bet my bottom dollar that you would have it on paper 2. This has been a common question that has been prevalent on all the AS tests. And it's too easy to get wrong. Okay, let's see an example of the most missed type of question. It will be right here. Not that it's difficult, but students ignore it because there's no line associated with it. But we're not in the business of looking at lines. We're looking at brackets. Brackets tell you have something to do. Label on the reef shark one visible feature only typically found in cartilaginous fish. It's not the dorsal fin. Dorsal fins are also found in bony fish. Also dorsal. It's not the caudal fin. Caudal fins are also found in bony fish. It's not the pelvic fin, and it's not the anal fin. Pelvic comes first, and if there's a second fin, then it's an anal fin. It's not your pectoral fins. All of these fins are things that are also in bony fish. Cartilaginous fish have an internalized lateral line, so that's not an external feature. Bony fish have an external one. Bony fish also have a gas bladder that helps them with buoyancy, and cartilaginous fish don't. They typically have a lot of oil in their livers, and that's going to help with buoyancy. Okay, it's going to be these right here. Those are gill slits. Bony fish have an operculum, which is like a bony gill cover. And when we label, we actually touch the structure that we're labeling. We use a pencil for that, unless you're very confident, and you should be. And then we label at the line. This label line needs to be horizontal. You don't want your Cambridge grader to be flipping your papers all different directions. Don't do that. You don't need to put it in a box, and certainly don't highlight it. You can highlight things that Cambridge has provided for you. They already know what those words say. They know it's there. You cannot highlight your own. The binomial name, bi-to-nomial name. Binomial name for a blacktip reef shark, here's an answer, is Carhinius. There we go. Melanopterus. Complete table 2.1, the classification of the blacktip reef shark. Okay. Here's another king situation. We got to know the order that this goes in. And so we do, like, say darn it, or some people say deer. Like deer, King Philip came over for good soup. Kingdom. Phylum, class, order, family, genus, and then species. You may be asked to supply this word, eukarya. That means this is an organism that has a nucleus. And you may be asked to supply this word, which is animalia. And they may give you more information, perhaps like at some time in development, this organism has a dorsal neural tube. And you would then need to know that that is going to be phylum Chordata. So these would be things that you could be asked to supply yourself. And so the genus and species, how do you identify that? Where is it from? You never have to memorize them. It's always given to you. You can tell because it's in italics. You do not have to write in italics. Some people naturally write slanted. You do not have to do that. It's not the expectation. But you should focus on the genus being capitalized and the species name being lowercased. Okay, got our 2 marks. We'll move on. Shark species have large amounts of lipids in their liver to provide buoyancy. State the names of the molecules that combine to form lipids. They're not asking for the elements. The elements in a lipid are the same elements that are in a carbohydrate, and that's carbon, hydrogen, and oxygen. They're not asking for the elements. They're asking for the molecules. This is from section 3.3, which is nutrients. And this is going to be a fatty acid tail and a glycerol. Here's the glycerol. And these are the fatty acid tails. Sharks use the ion phosphate. Give the name of phosphate and state one function of this ion in the shark. How would you know this otherwise? Back to what I mentioned on the first page, one of the salts you have to know is Mg, SO4, magnesium sulfate. This is PO4, phosphate. Phosphate's also mentioned in section 3.3 as well, with nutrients that are in the water. And then a function. So what can it do? DNA. DNA has a phosphate and a sugar backbone, ribose. And then it has one of your nucleic acid groups. And then this is like what joins, and it forms a double helix. But here is the phosphate. Phosphate. So we can say DNA, and if we can say DNA, we can also say RNA. Bones are calcium phosphate. I would stay away from bones because this is a shark, but they do have teeth. Also the cell membrane, or phospholipid bilayer. Some sharks are predators of ascidians. Some sharks, that means that they eat ascidians. And ascidians are, again, that's like your sea squirt. It's an animal, it's not a plant. And some of the ascidians have a mutualistic relationship with bacteria that live in their tissue. There's my bacteria living inside the tissue of the ascidian. The bacteria produce a toxin, and the toxin is only harmful to predators. Suggest how. So this command word suggest means this is not explicitly stated in your syllabus, but apply everything that you know to get this right. This relationship benefits the ascidian and the bacteria. I don't hate it. Okay. So how is it beneficial for the ascidian, and how is it beneficial for the bacteria? Beneficial for the ascidian. The bacteria prevent the ascidian from predators, or protect it from being eaten, or just add protection. The ascidian adds protection from predators. I'm sorry, the bacteria gives the ascidian protection from predators. This is because of the toxin. And the ascidian provides a habitat for bacteria. 2 marks, and that's what they're looking for. Benefits for both. Okay, now we have an extra 10 marks in. Okay, weathering and erosion. How does it give rise to the morphology? It's a common way they say that, give rise to morphology. Or how does it allow this rocky shore to form? It's how and describe. Describe is like what, but then that how kind of sneaks in and explain, a little bit of an explain, because explain is why and how. Weathering and erosion help form a rocky shore. Weathering. We have weathering is the breakdown of rocks. We'll need to include that. And if we're looking at the amount of marks, 4, we should be doing 2 and 2. Oh, excuse me. Chemical, organic, and physical. So we just need to bring in one of those. Here's your how. So it's a breakdown of rocks. How? From waves crashing We could say wave action. Constant drying and wetting from your tides. From chemical, RXN. RXN is reaction. Don't use that abbreviation. With salts. We could also say the salts crystallize in cracks and will cause it to break. Organic is also biological. We could say organic weathering from roots or lichen. Let's send myself something. This is some lichen. Actually, I took today. And the time is 1, 2, 3, 4. I see that time all the time. It's growing in a palm tree. And a lichen is it's made of two things. There's another good one here. It's made of a producer. Producer is on the inside of this. And what's on the outside is like a fungus that forms a crust over it. So it can be exposed like this and it's not going to dry out. This syllabus doesn't include like succession and ecology, like ecological succession, but lichen are always a great pioneer species. They're very tolerant to adapting to many different types of like drought conditions. So yeah, and lichen is a mutualistic relationship. The algae is going to provide glucose or organic material for the fungus, and the algae is going to be like the producer on the inside of this. And what's on the outside is this like fungus crust, and that's going to protect the algae and prevent it from desiccating. Erosion. This is the WIG. Water, wind, ice, gravity. And what is this? This is the movement of sediments or You don't want to say movement of rocks. You can, but like, do rocks really move like that? I mean, not really. They first have to get broken down. The movement of sediment or the transportation of sediment by wind, or you can say waves or gravity. They also allowed you to say like a comparative statement about deposition or sedimentation in erosion, or a statement about erosion actually being relatively low in a rocky shore. And that's because there's big chunks of rock. So large rocks cause lower rates of erosion just because they're, it's hard to move. And we don't really find sediment there. It's not settling. It's like constantly shaking a snow globe in a rocky shore. You're going to have large waves and they're constantly crashing. So any finer or smaller sediments that you have, they're not going to be able to deposit or build up like they will on like a sandy shore or in a muddy shore. You just have too much water movement. Mangroves. We love a mangrove. And within the rocky shores as well, I do have a separate lecture of rocky shore exam questions that I've compiled. And same with mangroves. I have a separate lecture on mangroves and then a separate lecture on the mangrove exam answers. And I think those are questions up through 2023. So muddy estuaries. An estuary is a semi-closed intertidal body of water, semi-enclosed intertidal body of water, which means it's not fully closed and the tides are going to affect it. And the water is brackish, which means it has a mix of fresh water and salt water. They have high sedimentation rates. You know if something has high sedimentation rates because you could dig a hole there. Can't dig a hole at a rocky shore. Can't get buried there. But you certainly can in a muddy shore, though that'd be gross, and definitely in a sandy. If you can have sedimentation occur or deposition of sediments occur, that means erosion is not going to be as strong. There could be some erosion, like at a sandy shore, a lot of them in Florida. We have a lot of wave and a lot of waves or water and a lot of wind erosion, but still you can dig a hole there. So that means that sedimentation, the rate of sedimentation is greater than the rate of erosion. The red mangrove propagules, little babies, settle in muddy areas. Describe 3 root adaptations that will allow the red mangrove to survive in muddy conditions. There's your water. Okay, mangrove roots. Okay, these roots, they're called prop roots. And we're in a muddy substrate, which means it is easily erodible. Granted, the way that mud can form is from extremely low rates of erosion. Like that sediment isn't moving easily. You can tell because it's still there. It's forming mud. In order for mud to form, water needs to be still for about 24 hours. So the prop roots in an unstable substrate, potentially unstable substrate like mud, the prop roots will provide stability. That's why they're called that, like it props it up, or anchorage. I'm going to say potentially, shifting or erodible. I'll spell that right. Substrate. And I say potentially because it could happen. It doesn't happen that often. You can tell because mangroves can grow there. That substrate is still there. The mud is still there. Okay, if we consider the liquid that they're going to be in, they're sitting in salt water, right? Well, it's brackish, but it's still salty. That's not really normal for plants unless they're adapted to it. But they're also adapted to being in fresh water. And one of the ways they do that, and you don't have to explain how, is their roots exclude salts from going in. So no salts can go in. They're able to filter it out. And because of osmosis of water and then diffusion of salts, that would naturally happen to species not adapted to be in this environment otherwise. And the last thing, which is, I call it like the little nostrils for the mangrove, they are called lenticels. And lenticels are all over these roots. If you think about a muddy substrate or like a salt marsh or something that's muddy, if you thought about how it smells, it's not going to smell that good. Why would that be? Because mud is a very fine sediment size, and that makes it not very permeable. So permeable to water, permeable to gases. So gases don't really mix within the substrate. Oxygen isn't going in, and gases might come out. Maybe they'll bubble up a little bit, or if you're moving that muddy substrate around, you could probably get a nice, delicious whiff. But otherwise, there's not really going to be a way to do any kind of gas exchange. So these are lenticels. Lenticels. Ability to do gas exchange. If you look on the mark scheme, instead of calling them lenticels, they called them aerial. Cool. Aerial roots, because they are exposed to the air. Okay, almost done with mangroves. We see the global loss of mangrove forests between 2000 and 2015. And we have some that are human caused and some that are natural. And our command word is suggest 2 different causes of natural mangrove loss. And then we need 2 different causes of mangrove loss due to human activity. This is from section 5.5 in the syllabus, and that is explicitly stated in the syllabus. Specifically, discuss the threats to mangrove forests, including temperature change, overharvesting, storm damage, and changing coastal land use. Discuss the importance of mangrove forests, including tourism, food sources, coastal protection, timber, fuel source, and biodiversity. So right there, we have some reasons of why humans might be using them. All right. The natural losses, it's got a lot. Something extreme. My favorite natural disaster to study is tsunamis. You could also say hurricanes. Just give 2. I'm going to give all the potentials, but you just give 2 on Friday or whenever your exam is. Give 2. Right now, I would list them all because it's good to at least practice what they can be. But if in actual exam scenario you're giving more than 2, it's not impressive. Why are you doing that? You could cause yourself to contradict yourself. You could write something that's incorrect. Don't do that. Don't do that. It's like they just asked for a cartwheel. You don't do a cartwheel and a back tuck. That's how people break their femur. Okay, anyway. This also is the same as just saying storms. Natural, always go disease, parasites, fires, like a wildfire, consumption. So maybe they're being eaten, and maybe an invasive species. The storms or hurricanes could cause coastal erosion. So they could be losing their substrate. Due to humans, so what would we use them for? over-harvesting. This would be the same as like the deforestation. For lumber, maybe biofuel. Climate change. Oil spills. Within that same climate change idea, but a separate mark. Sea level rise. Pollution, and then you would need to give an example. Well, here in Florida, where I live in Brevard County by the Indian River Lagoon, and when we have hurricanes come and we have a lot of like wastewater, like residential wastewater, that our water treatment facilities still need to go through, and they know that they're not going to really have time to do it. What if we lose some electricity? Maybe their facilities are going to, I imagine they're running on generators, but there's also going to be an influx of water. There's going to be a lot of influx of water, and that's really going to overburden our wastewater treatment centers. So what do? Do we allow everyone's house to flood and it's going to fill up with wastewater? It's going to go to like your lowest drainage area in the house, which for a lot of us is going to be our toilets or our bathtubs. Or do we make room for all this influx of water that's going to be coming through and allow the wastewater facilities to be able to take that on? And to have that space, we release our wastewater that we have not treated yet right into the Indian River Lagoon. All of it, untreated, toilet paper and all. That's common. And then we see afterwards, we might have some big eutrophication or, fish kills. That happens, and algal blooms. So that'll be my example. So pollution from wastewater discharge. I did say another one. Eutrophication. It's when you have an algal bloom and then all the nutrients gets used up from all the algae. Algae die and they sink, and now your bacteria have a massive marathon to run in terms of decomposing the dead algae that just sunk. And the bacteria are going to be using a lot of oxygen to break these things down. And now you're not going to have, you don't have this big producer population. The algae was there, but now the algae died. They died because they overproduced, and they overproduced themselves. They reproduced too much. There's not enough nutrients to support them. You can also have light blocking from any seagrasses that are at the seabed, or the algae could cover the seagrass blades and, seagrass leaves, not blades. They cover the seagrass leaves, and now it prevents them from doing photosynthesis. And we're not going to have any added oxygen. Oxygen that's in the water is going to get used up by bacteria decomposing it, and that will cause a lot of fish to die and potentially a dead zone for a moment. The syllabus also mentioned tourism, so it could be clearing the land, for tourism, like resorts, golf courses, shrimp farms, housing. Some math. Calculate for the period 2000-2005 the loss of mangroves due to natural causes as a portion or a percent of the human loss causes. So they want what percent is the natural causes of the human causes. What's coming after the of is going to be like our whole, right? Portion over a whole. So natural causes over the whole, over the human causes. That's how they want us to do this. All right, so we need to be able to read this. We need natural divided by humans. Our natural causes from 2000 to 2005. We got to zoom in. We got to be perfect. You got to know what you're counting by. So we go from 0 to 500. And we have 1, 2, 3, 4, 5 lines in between. So we're taking this number 500 and we're dividing it by 5 lines or 5 boxes. And here each box equals 100. And I'm saying like this is a box, so like this area. And when I do this, I just leave it here next to the axis so I know what I'm counting by there. Human causes is what I made this yellow. And so we have, here's 2000 minus 100 is 1900. And then natural causes is the darker gray. And we're right here. I'm just a little crooked. All right, here's 1000, 1100, 1200. All right, and then the final thing we got to do is times 100 so we can get it into a percent. We're essentially doing 12 divided by 19. And then times 100. 12 divided by 19, you'd probably get 0.632. Times 100, you'll get 63.2. And they wanted 3 significant figures. 6, 3, and 2 are significant. Where are the marks coming from? Showing your work. So all of this is 1 mark. Having the correct answer is a mark. And then having the 3 significant figures is the last mark. And they already have percent there for you. Okay, I believe this is our last question set before we get, into our extended responses. And again, we have the most missed question. We look at brackets and we don't miss those. Label the Pacific and the Southern Ocean. I'll do the Southern Ocean first so you can see the boundary. Southern Ocean needs to be below Africa. Below Madagascar, not Madagascar, New Zealand. Stay below Africa. I don't edit these, but I realize I call this Africa. That's embarrassing. It is what it is, whatever. Also, if you look at the time, 12:56, bless my own heart. This is South America. North America. Asia. Europe. Africa. Madagascar. New Zealand. Australia. Oceania. Prove myself. Okay. This is our Southern Ocean. And it could be anywhere in this area. You didn't have to write it so big. It's anywhere in this area. And then Pacific. This is sometimes a hard one for Americans because we're used to seeing North America and South America as the center. And we're used to seeing like here where the Atlantic is. We're used to seeing that as like the center. Poor us. Pacific Ocean is going to be in the middle. All right. Reading graphs. We're looking at the relationship between temperature and depth for one area of the ocean in the northern hemisphere during 4 months out of the year. Sometimes before I look at the question, I try and make sense of like, what did I just look at? Can I make sense of this graph on its own? Okay. In March, we're not even at 5 degrees Celsius. That's rough. That's cold. And this is like our surface waters right here. It's cold. We don't really see a thermocline. No thermo. November, a wee bit different. So November, we have some stability. It's a little bit warmer. And then we see a thermocline, right? This big transition for where there's a drastic change in temperature with depth. But even though it could be colder in the northern hemisphere in November, water has a high heat capacity, so it's still maintaining its temperature right here. July, we're heating up. This doesn't need to go in any like month order, so don't let that confuse you, that it goes March, November, July, August. These are just put here based on their temperatures. July, we're even warmer. And because of this warmth, our thermocline ends up being a bit shallower. Notice in November compared to July, like this has moved up a bit, the thermocline, but that's because there is now such a drastic density difference because of the temperature change. It's much warmer. August, we've had May, June, July, and then August. We've had time to heat up. August is the warmest. And they said it's the northern hemisphere, so this would be cold winters, getting warmer in the spring, hot summers, getting cooler in the fall. Okay, and then again after August, we would go September, October, and now there's the November. November is losing some heat, but doesn't lose it all because water's a high heat capacity. And our exam question. Explain how. So this is a why, a how, give reasons for. How it shows that the data were collected from a temperate region and not a tropical or a polar region. So we can answer this and say, here's how I know it's temperate, or this is not tropical because a tropical would be blah, blah, blah. Polar would be blah, blah, blah. And we can answer both those ways. Temperate. Temperate has seasons. This is not like Florida. If you're a student in Florida, this is not us. We have a subtropical climate, and it's only because of the jet stream and the fact that we're just a little peninsula sticking out in the water. And yeah, we're surrounded by warm Gulf. We're surrounded by the warm Atlantic. Truly, we shouldn't be as warm as we are, but the water allows us to be. Okay, so how do we know that this is from a place that has seasons, essentially? And we want to use that figure. So come with receipts from using that. All right, there's a plethora of answer types. Okay, so in the tropics, and I'm just going to give some comparative statements. the surface temps are high throughout the year. We could even say higher, giving like a comparative statement. Or you could talk about polar is lower temps throughout the year. Okay. Likewise, we can talk about what the temperate has. Temperate is seasonal. And then how is that evident in this graph that we see? And the thermocline changes throughout the months. I labeled them. In terms of the thermocline, in the tropics, there isn't a large thermocline or like a large temperature change, a large thermocline. Due to warmer temps year round. And if we see like, I'm gonna zoom in here. For this August one, we're warm at the surface, right? Because we've been warming up all summer. And then, oh, fun, that's fun. And then we hit this big temperature change. But why was this a big temperature change? Because we're not that warm all year long. There's other times like, ooh, look at March. There's other times like March where it's very cold. So, you know, we're just heating at the surface. We're just gonna have this drastic change. And it's not that drastic of a change in November. We're getting colder heading into November. We're still hanging on to a little bit of that heat that it took in throughout the summer months. And then finally, between November, December, January, February, we hit March, we're cold, cold, cold. I can talk about the polar regions are cold year-round. Now, I'm not just going to leave with that statement, right? Because we kind of said the same thing up here. I need to talk about my thermocline. And the thermocline looks like the one from March. There's really no thermocline, right? It's none. We can use data. If there's data you can talk about it. And here you don't have like any other increments other than being able to kind of guesstimate the middle. So you can kind of get some actual numbers to talk about. But we could talk about the range in surface temperature. So for example, right here, we would say it's like a 4.5. And then it's not exactly 14, but it's pretty close to 14, right? Yeah, it's really close to 14. Yeah, 13.95. You can call it 14. About. So, like, the temperature range. 14 degrees Celsius minus 4.5 degrees Celsius. 9.5, the temperature range. Now that at the surface would not be that way in a polar climate nor in a tropical climate. Tropical would not have that big of a difference, and neither would your polar. It's just stay pretty cold. But let's talk about it. In polar and in tropical, or you could say or tropical, either one. Polar, tropical climates or regions, there's minimal surface temp changes. Throughout the year. Now I need to separate this statement from kind of what I said in the beginning. Tropic surface temps are higher, or in polar, the surface temperatures are lower. This is, I need to make this unique, and here I'm going to talk about some numbers. The temperature range in figure 4.2. It's 9.5 degrees Celsius, right? So that separates that last statement from what I said in the beginning. I'm really talking about data with this. All right, and then one more that we don't always think about, and I think this is because in Florida, we don't really recognize March as like a stormy month, but that's because Florida, we don't really consider ourselves to be in the temperate regions because we're over here, we're warm year round. Again, poor us. I live like right there. But warm year round. I used to live up here. In the winter time, or in March, winter is time for like winter storms to go through the oceans. Now we don't always see this. We're a little bit more stable where we are, but in general, winter time is like a stormy time. And why am I saying that? Because if you have a lot of mixing, like with waves, right? We're having a lot of wave mixing, a lot of turbulence. We're not going to have this like very stratified and sectioned off water column with different temperatures. It's going to be mixed. It's going to be mixed. It's going to be mixed. So we're kind of mixing those temperatures there. That is like in general for oceans for the winter, not Florida. And if we remember it, remember it. If you don't, you have plenty of other things you could talk about, and that'll be the last mark that I put for this one. March has little to no thermocline. due to winter storms. Mixing the water column. Amazing. Using figure 4.2, same thing. State the month in which the water density is highest at 20 meters depth. All right. I need to change my color. Here's 20 meters. It's just a little bit above it. Water density being the highest. Well, there's only one way to know. Density is caused by salinity and temperature and water pressure. Well, water pressure is not an effect. Water pressure is an effect at the seabed, but we have temperature here. And we know that low temperature is going to cause high density. Makes the water heavy, it's going to sink. And so our lowest temperature here is going to be in March. Explain how and why primary productivity is different between March and August. Okay, so we need to say how is it different, and then we need to say why is it different. Primary productivity, that is a definition that we need to know. Productivity, primary productivity, you probably think primary producer, you're on the right track. Primary producers do photosynthesis. And so this is, let me make this a little bit thinner. This is the rate of photosynthesis. A better way to say it instead of rate of photosynthesis is rate of biomass, glucose, biomass production. So rate is how fast, how much biomass they're producing in a certain amount of time. Rate is always including time. Rate includes time. So how fast and how much glucose or biomass is being synthesized in a certain amount of time in a certain area. Okay, and its units are going to be glucose mass, so like maybe kilograms per area per time. It's typically like the time might be like over a year where we're going to consider all the seasons. Okay. You could go both ways with this. So how is it going to differ between March and August? March, it's really cold, but we could talk about storms causing upwelling and moving in nutrients. So these winter storms could be producing offshore winds. Maybe you're going to start to have some melting, and that's going to bring in nutrients with the water melt. Remember, upwelling brings cold, nutrient-rich water from the seabed to the surface, and those nutrients are directly used then by producers. You could also talk about August having really high light intensity and longer days, right? Our days are longer in August. That could cause more productivity. So we could go either way with it, and so I'm going to do a T-chart and split this. For this question, you want to kind of just stick to one side. And we got 4 marks. So if you're going to say it's high in March or it's high in August, that's fine, but just try and stick to one side of this. Okay. Just giving a statement of what you think is going to happen is not going to give you a mark, but I'm going to preface it. High in March, which is going to be low in August. You're not going to get a mark for that, but now, because it's the explain how and why. Productivity is an important definition. When in doubt, you see a definition in an exam question and you're in doubt, like go with its definition. This is an important term. So we can start with that. Rate of biomass production per area per time. Upwelling can increase the nutrients. In March, or this would be like the spring for temperate areas. Or, and you wouldn't put both of these, you wouldn't also include or, I'm just saying there's another way to think about this. By the time it gets to, by the time August comes around, and right, we're saying that August is going to be low in this scenario. Like, why would August be low? Oh, excuse me. It's because throughout the summer and the spring, the nutrients were all used up. And so when it gets to August time, there's really not really any nutrients remaining to cause productivity to be very high. We're just thinking in different situations of how these things can be true, just applying science concepts to it. And this would be like within the same mark because you're saying this or that. In August, nutrients have been used up. PP, primary production, is low. And they were used up like in the spring. So like March, April, May, June, July, and it gets to August, those are all used up. Some more things we can say, and I'm going to move her down here, which is fine. You can do this in your actual exams, right? This is question number 4. I would say 4BIII continued. If you didn't think about upwelling, you could say nutrients increase due to runoff in the winter. From melting snow or ice. If you want to bring up the storms again, like bringing runoff, that's fine. In the springtime, light intensity begins to increase. It's not its highest. It's certainly not its highest. It'll be highest in the summer, but it's starting to increase, which increases photosynthesis. Okay. That'll be good. We'll go to the other side. High in August. Low in March. You don't get a mark for that. You're just kind of categorizing it. Same thing. We can move this definition over here. Get a mark. All right. I think most obvious, there's colder temperatures in March. Which decrease the rate of photo. If you really want to know why, it's slower enzyme activity. You could say the reverse argument. You could say in August, there's warmer temps, which is going to increase the rate of photosynthesis. March has shorter days. We could say less hours of sunlight. Which decreases photosynthesis. And again, that's what primary productivity is. It's the rate of photosynthesis, how fast it's done. That's like the duration of the light that they get. The duration. We can also mention about the light that they get, right? You could have shorter days with really bright light intensity, or you could have shorter days with low light intensity. So we can talk about light intensity. You can talk about light intensity in August. You can talk about light intensity in March. Which decreases the rate of photo. And obviously you'll want to put photosynthesis on your exam. All right. So you can go either way with that. State the word equation for photosynthesis. Guaranteed, if it's not on paper 1, it's going to be on paper 2. They could also ask you to do it for respiration, but if you know photosynthesis, then you can also know respiration. It's just backwards. Flip your arrow. For photosynthesis, plants need, it's the word equation, so they need water. They need carbon dioxide. And if you want to put like light here, you totally can. But what's expected is the water and the carbon dioxide. And it releases oxygen and glucose. Releases oxygen, but synthesizes glucose. There you are. And then for respiration, you literally would just say backwards. You would say, we eat sugar, we eat glucose, we breathe in oxygen, and we get ATP. We breathe out CO2, we breathe out water vapor. Plan for photosynthesis. I say that every year, and then I still have students that are just putting the most wild things. We've made it to the extended response. All right, so we got coral polyps, rocky shores. We love it. We reverse global conveyor belt. And then what is El Niño doing to Australia? All right, coral polyps have two methods of obtaining nutrition. I'm going to sketch this out towards the bottom, and I'm going to do a T-chart though. You can definitely do this as well. You can create graphic organizers. You can make a chart on your exam. I think it keeps you a little bit more honest and keeps your thoughts organized. All right. What's all this? Wild. Oh, interesting. Interesting. Okay. I'm distracted right now. I'm so sorry. I can fast forward this. I'm not even going to edit it out either. Wild. Okay. It's this random Walmart order, but it's from Easter and getting Easter eggs for the yard. Okay. I'm just going to take 1 minute before I answer this, and I can't pause it. If I pause this, there's no such thing. I have to stop it and then restart it, and I would never. Okay. We're at the home stretch. All right. So notice if you're exhausted right now, feel that, right? You don't want to do this. Get exhausted doing the beginning parts of the test because you feel confident about it. And we would much rather want to answer short questions, for sure. Label things, fill in the blanks. It's a dream. We all want to do that. But if you're exhausted at this right now, this is where it's going to make or break. We want to put all of our effort, the maximum effort, into being able to answer these extended responses. And there are a lot of marks. 19. And then 6, you got 15, and another 5, you got 20. My gosh. Okay, we're going to sketch out a coral polyp. This is something that I encourage my students to do. We try it 3 times on a Saturday school study session, and it doesn't really take more than 3 times, as long as you take breaks in between. But there was a couple of years ago an exam question, just finding space, where you did have to describe the structure of a coral polyp, and so you'll never catch me slipping again. Okay, we'll start from the top. Okay, these are tentacles. And do you have to draw this? No, but it's a nice reminder to yourself. Tentacles are going to catch prey and then put it in their mouth. And then they have this body. They have this thin wall, this thin body wall. The thin body wall is called the theca. The theca is the thin body wall. Okay. And these have to attach to a hard substrate, right? So they attach to a substrate. And they attach using, the word basal means base. right? Basal is base. This area here where they're attaching, it's a basal plate. Basal plate. And then all of this forms this cup. C, U, and P. And that is called I don't like the way I'm writing that. It's called a calyx. Inside of here, they have a stomach. And so tentacles grab food, right? Like little zooplanktons. And then tentacles put in the mouth. And then it's going to go in, this is going to go into their stomach. Inside their stomach, they have gastric fluids that are going to digest or break down their food. So one of their ways is by using tentacles. If you think like we don't want to touch a coral, we also don't want to touch an anemone, we also don't want to touch some jellies. Why don't we want to do that? Because they are in phylum Cnidaria. And that's with a C. Cnidaria. Which means they're cnidarians, and we term them that because they have nematocysts. Cyst means cell. Nematocysts are stinging cells. And so I can actually zoom into the tentacle. I don't actually have to redraw it, which is cool. So on their tentacles, they have this like first layer of cells. Okay, and they can release toxins from them. And then like inside one of these cells is like this harpoon-like structure. And it's like, it has like a barb on it. And that's what that's why they sting, but like, or that's actually their method of inducing a sting. So and it's kind of like coiled up. So once it gets released, like it comes out with a lot of pressure. And yeah, there's like a barb on it. So it punctures into their prey item and releases a toxin which will stun it or it will kill it, and then they'll put the tentacle towards their mouth and feed off that. When they're feeding off this, right, this would put the coral eating at trophic level 3. Why do I say that? Because is why, just because. Okay, let's assume it's eating like a zooplankton. Oh, like a little copepod. Little zooplankton. Well, zooplankton eat phytoplankton. Phytoplankton is trophic level 1. And zooplankton would be trophic level 2. And then whatever is eating the zooplankton is trophic level 3. So here our coral is feeding on trophic level 3. But wait, there's more. Not only do they have these like cells in the outer layer that have nematocysts in them, they have a very thin body, so this isn't deep. The next layer of cells is what actually gives them all their fun color. Inside these cells, they have their zooxanthellae. And again, this can provide them with like all the vibrant colors we imagine corals to have. The zooxanthellae have different pigments in them that will absorb different wavelengths from the sun. And like, I know we're familiar with chlorophyll. Chlorophyll absorbs your blue and your red wavelengths and reflects green, which is why we see green. But inside of here is zooxanthellae. That's going to be too crowded. Zooxanthellae. Zooxanthellae live inside of the coral polyp tissues. Just one of these is called a polyp. Just like one flower forms a bouquet, one polyp is a part of a bigger colony. So a colony of coral polyps, we just call them a colony. Zooxanthellae does photosynthesis. And that puts zooxanthellae at a trophic level 1 because it's a producer. And this is a mutualistic relationship. Zooxanthellae will get like a habitat inside of the coral. Zooxanthellae and coral will be growing close to where like the light penetration is high, and they do photosynthesis, and they need to be within like 15, 20 meters of the water. Like that's it. They can't be very deep. So they don't even have the entirety of the photic zone. It's relatively shallow for them. And coral, right? Again, the salts that are very abundant in the ocean, you have sodium carbonate, it's like sodium chloride, magnesium sulfate, and calcium carbonate. Shells and coral skeletons are made of calcium carbonate. But what we notice here is carbon. There's carbon and oxygen there. Doing photosynthesis, right? Producers need carbon dioxide. They need a source of carbon so they can make glucose. Glucose is C6H12O6. The C and the O are going to come from carbon dioxide or the carbonate, and the H comes from water. This oxygen that gets released is like the first order of business. Absorb light, split a water molecule, and that's the oxygen they get rid of. So all that being said, the coral is a good source of carbon and oxygen for the zooxanthellae to do photosynthesis with. Finally, mentioning that zooxanthellae is a producer, they do photosynthesis. That puts zooxanthellae in trophic level 1. Well, I use the example of like this is like a live-in chef in your house. The chef is going to make the food. The chef is going to taste the food and probably eat it first as well, and then you get to eat. So zooxanthellae is trophic level 1, and then the coral will get a lot in the majority of its nutrients from the zooxanthellae doing photosynthesis. It's going to get a lot of its nutrients directly from that glucose being made. And so when this is happening, and it happens a lot, it's, their photosynthesis can occur for longer periods of time throughout the day than just this straight feeding with its nematocysts on its tentacles can occur. Because corals are naturally filter feeders. But if there's not much to filter out, they would just die. So the zooxanthellae is like taking the brunt of that to produce some glucose and some food. And anyway, when it's feeding off that, then that puts the coral at trophic level 2. Because it's feeding right after the producer. Woo, okay, so we're going to split this up. I'm going to talk about feeding with nematocysts, and then I'm also going to talk about the zooxanthellae. Okay, I'll do the zooxanthellae first. And if you're wondering, do I have to spell this correctly? This is not a spelling test. It's not a grammar test. Phonetic spelling is good. You cannot put zooplankton, of course, but phonetic spelling can work. So describe, which is like what are they doing to get their nutrients, and then explain like how that's giving them nutrients. Okay, so just stating zooxanthellae is going to be a mark, but just for my categorization, I'll repeat it. Zooxanthellae perform or carry out photosynthesis. They have a mutualistic relationship with coral. Okay, and that's all from Unit 5.2, which is Tropical Coral Reefs, which I also have a lecture for. Coral live in shallow water, about 20 meters. You don't have to include the depth. For highlight penetration or highlight availability, xanthelle produces glucose. Okay, and then just to tie this up, I'm going to finish with this statement that says essentially that the coral is going to get some nutrients from that glucose. Not xanthelle, sorry, coral. Asking about trophic levels is not on the, like mentioning trophic levels was not on the mark scheme, but I think it's a brilliant thing to say anyway. And so I'm going to mention the coral being on trophic level 2 in this situation. It's not on the mark scheme, but again, we won't know that. And now we're going to talk about its tentacles. Because they naturally are filter feeders, but if there's nothing to filter out, they would not be able to get energy. All right. Coral polyps, you just call them corals. Have cnidocytes. You can also describe that as stinging cells. Cytes is a cell. Cnido is, again, what puts them in phylum Cnidaria. These are located within their tentacles. Toxins get released into their prey. From the cnidocytes. Parentheses means it doesn't have to be there. I'm just adding context to it. The toxin stuns, kills, or immobilizes the prey. The prey is sent to or goes into the stomach I'll say the mouth first. The mouth. Then stomach for digestion. The polyp uses the nutrients, or you could say like the energy, from the prey. So there's 6 marks on the tentacle one, 6 on the zooxanthellae one, and I'll also include here, just to be thorough, corals feed on trophic level 3 in this scenario. And I explained it right here. So they're eating, like, you know, these little things that are falling down, little zooplankton, or maybe it's like fish larvae, fish eggs. Then there you go. They're still feeding at a higher trophic level. All right. These will be faster than you think. Let's do it. So exposure time in air. Dissolved oxygen concentration. If it's dissolved, it's in the water. And competition are factors affecting distribution and abundance. So the amount and then how they're like sorted of organisms in different zones of a rocky shore. All right, we should be thinking waves, and we should be thinking like vertical zonation. Explain, so why and how. Explain how these 3 factors, exposure time in air, dissolved oxygen, and competition, affect the distribution, so how they're sorted, and the abundance, the amount of organisms in different zones on a rocky shore. So she's loaded. It's a loaded question. We need to talk about this. We need to talk about this. We need to talk about this. It needs to be we need to compare it to the distribution and the abundance of organisms and in different zones. Yikes. Okay. I wouldn't want to do this without a picture. So we're going to throw in a picture really quick. Give yourself a rocky shore. All right. Up here, here, and here. So it's my high tide, or we call this the upper shore. Here's your mid tide. These organisms are submerged longer than the high tide organisms. Organisms at high tide are only submerged during high tide, and they're submerged the most during like a spring high tide. We would call this also the middle shore. And down here is our low tide, and we would call this lower shore. And then anything down here will have like a tide pool. Tide pool is like the first class of the rocky shore. Everything would want to be here. Also called a rock pool. Okay, competition is going to be highest where they're going to be underwater the longest. So competition is going to be high here. High competition. In order to live down here, you need to be able to compete for space. And some organisms can't do that. So they will take their place higher up the shore. Yeah, that means they're going to be affected by being exposed and being out of water longer, but they also don't want to die. So it's kind of a, comparison of how much they can compete or they don't want to die, and how well they can tolerate the abiotic factors they're going to endure from being out of water. Higher up the shore, so the ones that are going to be out of water longer, these are going to be shelled organisms. They're going to be able to close their shell. Some organisms can move, like your sea star. Sea star is like the bully. A sea star is able to move. A sea star definitely doesn't want to be out of water long. If you can move, you're going to be moving yourself down here to where you're going to be in water longer. Organisms down here are like softer body things. You can also have like some octopus. Oh, geez, 8 legs is a lot. Little siphon. Softer body organisms are down here. You're going to have some anemones. Those are very defensive, right? Those are also cnidarians. They have stinging cells. They are soft bodies. They're going to want to be underwater. Up here, you're going to have like a lot of your barnacles. You can also have mussels. Limpets. And up here is a splash zone. These organisms are only going to get splashed with water, and that's during your high tides. They might be submerged if you have like strong onshore winds pushing water up, or you have a low air pressure system that allows water to expand, so that would be like a hurricane, big storms. Okay, in general, we're going to have to kind of introduce like this distribution and abundance thing for the rocky shore. And they also talk about how they sort themselves, so that needs to be mentioned as well. Let's do it. I'm just going to put org, organisms. Organisms, org. Zone themselves in a vertical, like up and down zonation pattern. Explain, right? Or how do they do this? This is based on their ability to tolerate abiotic factors. When out of the water, or when they're not submerged. Okay, advice. It says on your syllabus to be able to have organism examples and what their adaptation is to tolerating living in this kind of zone, right? We saw one with mangroves and how they have adaptations on their roots. In sandy shores, organisms are burrowers. They're camouflaged. They filter feed through the sand. They need to move up and down with the tides. Those things will also be shelled type organisms, but they could also be like worms, and they're able to burrow. There's so many we can know in a rocky shore. So I'm going to split this up into the exposure, time, and air, dissolved oxygen, and competition. And just so you are expecting it, exposure, time, and air will have the most amount of things you could write about, because that really is going to be like the crux of their problems because of this tide situation. And, got to consider within the tides, you could have, diurnal tides. Most tides are diurnal, which means there's 2 high tides, 2 low tides in a day. So there's going to be 2 times organisms in the high tide zone are going to be underwater. The 2 times they're not going to be underwater. Most of the time they won't. They will only be submerged twice a day just for a little bit of time. Lower tide in the lower shore, they're going to be underwater much longer. And we could also talk about, the difference between spring tide and neap tide and what that's going to mean for them to be underwater. So I'm just going to sort this for exposure time and air. All right. Use examples as often as you can. And we're going to also talk about the different zones. We're going to use those names as often as we can. And we're going to touch on the distribution and abundance. I'm going to tie it into the exposure time and air. Okay. In the upper shore, or you can say like a high tide zone, organisms, ORG. Have the greatest exposure to air. You could say they have less water coverage, or you could say the reverse argument. You could also say in the lower shore or low tide zone, organisms have the least exposure to air. Why does this matter? Desiccation. Longer time exposed to air increases the risk for desiccation. 2 C's, 1 S. We can also say they have to be adapted to avoid desiccation. Okay, I'm going to add in an adaptation. Desiccation is drying out, but desiccation is a term from the syllabus, so we should definitely use it. Organisms, I'm going to say the limpet. Clamp their shell to rocks to trap in moisture. Longer time in air. Exposes or causes, or whatever word you think is better, a greater temperature fluctuation. Water has a high heat capacity, and water doesn't change its temperature quickly, but air certainly can. Okay. We can talk about the different types of tides. During a spring tide, where we have the highest high tides and the lowest low tides. I'll talk about the lower shore now. In a spring high tide, the high tides are a little bit higher and your low tides are a little bit lower. And so I'll just mention the lower tide area for now. During a spring tide, organisms in the lower shore or the low tide zone have more exposure to air than during a neap tide. In fact, a neap tide, they have more water. And shorelines with diurnal tides, you could also talk about, oh shoot, I'm sorry. I think before when I said, hold on, notice the time, it's 2:03. Before when I said diurnal tides, I said it happens twice a day. No. Semi happens twice a day. Like a semi-annual sail would happen twice a year, even though it's always more. Semi is 2 highs, 2 lows. So we're going to correct that. And you would be writing in pen, and if you notice you made that mistake, you're just going to scratch it out and you're going to put in the right answer. And shorelines with semi-diurnal tides. There we go. Organisms are exposed to air 2 times a day. Submerged 2 times a day. And just diurnal tides, this is only going to happen 1 time a day. 1 high, 1 low. It's not very common. And just for a good time, I'll give another example. In your lower shore, or like your lower tide zone, organisms may lack shells and must move to stay submerged. Perhaps we want to say move to a tide pool, because that'll give us another mark. And I'm going to give an example. Like a sea star, or you can call it a starfish, I just can't. All right. There's 2 more sections, and those don't have as much writing, but we can talk about, I'll hold on to it. I'll hang on to that. We need to mention the distribution and abundance, but I'll bring it up with the next part. So we took care of exposure, time, and air. We need to talk about dissolved oxygen. And it is appropriate for you to sketch anything out on your exam as well. It's fine. Dissolved oxygen. It's not oxygen. It's dissolved oxygen. So we need to be considering that this is going to be in the water. This one is easier than you think. Organisms. So like this is going to be like the Y. Must extract, or you say absorb, O2 from water. And anytime we're talking about oxygen, we need to talk about respiration. All right, and then I'm going to link this to maybe how it can fluctuate. When the tide returns, O2 concentration, CONC concentration, increases from wave turbulence it's not in the mark scheme, but I don't see why you couldn't put something like in a tide pool or a rock pool, the O2 concentration will decrease as the temperature increases. Also, if you have evaporation occurring, and most of the time you will, it's going to increase salinity. And when salinity is high, your gas solubility is low. There's just not enough space to fit oxygen in there. So that will be another reason why it could be low. And we gotta take care of one more. We need to talk about competition. Oh, that's cute. That's cute. Guess I'll finish it down here. All right, there's two kinds of competition we can mention, and right when organisms are going to compete for resources. From section 4.4, we have two different kinds of competitions. We can talk about interspecific and intraspecific competition. So another definition is between two different, different species. Something they could compete for, space. Intra-specific competition is between the same species. Organisms will compete for mates or food. You could say food here as well. Compete for like oxygen, compete for nutrients. Conditions are most favorable. Blessed day. What I'm going to talk about, right? So there's high competition right here. Yeah, so I'm going to talk about. Which makes competition here high. Likewise, I could also say the splash zone is harsh and has little competition. Y'all, we got one more thing to write for this. It's about distribution and abundance. And all I'm going to say is the abundance of species and where most of them are distributing themselves is towards this lower shore tide pool area, right? That's like where the best seats are. Species abundance and distribution increases down the shoreline as organisms have access to longer times or duration in water. Okay, last questions. I bet I couldn't do this. Maybe I can. We'll see. I did. Oh, this is wonderful. Okay. All right. We have the location of the Greenland ice sheet. It's right here. The global ocean conveyor belt is a constantly moving system of deep and surface water. This deep water is from thermohaline circulation. Thermo, temperature, haline, salinity. So this is all density based. Some scientists believe the global ocean conveyor belt is slowing down due to the melting of the Greenland ice sheet. Suggests why the melting of the ice sheet could slow down the global conveyor belt. All right, so in order to be able to, kind of understand this, we need to consider what happens normally in the global conveyor belt. And let me zoom in. All right, so we start in the North Atlantic. And it's so cold. This is normal, right? This is normal. This is normal. It's so cold in the North Atlantic. I want this. I don't want that. Okay, so cold in the North Atlantic that we're going to get ice to form. Great, lovely ice. If ice is forming, that means it's really cold, right? So low temp equals high density. That's sloppy, forgive me. And if we're forming ice, that means that fresh water is being taken out, so increased salinity. Increased salinity also means high density. When water is dense, it sinks. This is downwelling. Okay, and this is like the first domino to like knock over all the dominoes. Okay, so just focusing in this area, if we're melting, then we're adding fresh water to the surface layer. So this high salinity, high density isn't going to happen. Water's not going to sink. There won't be downwelling. And sure, salinity could increase if there's enough evaporation, but there won't be enough evaporation to get it to that same level again. We're going to have water floating. If you're thinking, yeah, but if we're melting ice, couldn't that cause like the water in that area to be a little bit colder, you could also go that route too. You can also get marks for saying that if the melting ice is going to make the water colder, and that's going to decrease temperature, obviously, and cause high density, and maybe there's still some sinking, you can also talk about that. All right, and it'll take longer for, ultimately, with all these factors happening, for water to become dense enough to actually sink and start this whole process. So we start with the melting sea ice. Releases or adds fresh water. If you're going to say it dilutes it, make sure you prove that you know what that means, that it's going to be releasing fresh water. This decreases the density. Surface water will float. The salinity, and it doesn't have to go in this order, it can go in any order, will stay lower longer. To add to that, evaporation won't have, because there could be evaporation, but it won't have the same effect on density. Parentheses, just add context, because water is heavily diluted. I can say that because I already said fresh water. Therefore, it will take longer for water to become saline enough, or to increase in density. I'm sorry, to like increase in salinity to cause sinking. We need that sinking, because that sinking is that first like domino knocking down all the dominoes. This is what is like starting to push water globally. Let me back up and then do it again. Downwelling won't occur. So, we can refer to that as the driving force. The driving force of the global conveyor belt is hindered or stopped. But melted ice can decrease the temperature of water, which increases density, and water will sink. So we're kind of looking at both scenarios here. Oh my gosh, this is like a 5-hour video. Great balls of fire. Okay, we got a fresh one here. El Nino. You know what I want? What does that do? Oh my gosh. Well, isn't that incredible? All right. I want to crop it. Can I crop it? Yes, I can. Yes, I can. Yes, I can. Okay. I think this will be better to see it this way. Trust. Okay. Yeah, I prefer to see it this way. All right. The effects of El Nino on the east coast of Australia. Great balls. All right, let's do this. El Nino. All of this is occurring. We want to consider over here off the coast of Peru or Ecuador. All right. This is all about the trade winds, equatorial trade winds. Equatorial trade winds follow the trade route, and it goes never eat soggy waffles, northeast, southwest. Okay, it goes east to west. So our winds are going to be going this direction, right? This is a normal scenario. We go from here, we blow surface water this direction. This is normal. This is not El Nino. This is normal. When this happens, we have winds pushing off the shore of Peru. And if we have offshore winds, it's going to cause low water pressure at the surface, which causes cold, nutrient-rich water to move up from the seabed. And it's going to bring nutrients with it, and it's going to go to the surface. It will decrease the temperature over here in South America, and it's also going to allow there to be a lot of nutrients for a lot of primary productivity, and you have like a feeding frenzy. Now we're pushing this warm water in a normal scenario. We're pushing warm water over towards Australia, Asia, and I'm going to call that Australasia. So here we have warm water piling up. This is a normal scenario. This is what normally should happen, not during El Nino. And when you have warm water piling up, that heat has to go somewhere, okay? And it's going to go to the atmosphere. All right, we have heat there. It's going to cause actually a lot of disturbance, a lot of storms, and that water vapor that's evaporating because it's very warm. We're going to have some clouds, and what are clouds going to produce? A lot of rain. This is good, right? Because Australia is sometimes on fire. So Australia gets to have some rain, hooray. We get our rice crops over here in Asia, get a lot of rain, and it's great. There's food here from our crops. We also have food in the South America area because they have like their oceanic food web is being taken care of with all those nutrients, feeding producers. It's a good time. But during El Nino, there's La Nina. That's we have strong winds. El Nino is weak. We have weakened winds. So now I'm going to play devil's advocate, and I'm going to get rid of all this. El Nino. There's we can describe this happening in two ways and the effect will be the same. We can describe it happening two ways, the effect will be the same. So I jokingly say in class, this is the weak boy. La Niña is the strong girl, and she has a stronger push of air across. So you have even stronger effects of what I just drew. Stronger upwelling, way more water piling up. All the effects are going to be exacerbated. El Niño is weak. So instead of pushing this warm water off the coast of South America, here's all your warm water. Instead of pushing it over to Australasia, we have weakened winds. And so like boop, boop, we're gonna push it just a little bit. Just a little bit. Okay, that is a scenario. Or, hear me out, another way El Niño happens is when the trade winds reverse. You can go either way with this. If they reverse, you're gonna have the same scenario. These weakened winds, they're not strong enough to force upwelling. So upwelling doesn't happen. But if I have winds that are reversed and they're coming this direction now, they're going west to east, guess what? This is an onshore wind. It's blowing on the shore of South America. Upwelling still won't happen because you need offshore winds to force that. You can talk about this either way. I'm going to talk about them being weak. Well, if they're weak, we don't have any of that warm air blowing across the surface of Australia. That warm air helps form like the rain clouds and like the rain system that we have in Australasia, right? The Australia-Asia area. It helps form the rain clouds there. So if during El Niño, we're not going to have rain there. The rain is going to be here, where we don't need it to be. Because when it rains here, first of all, it's going to cause lower light energy in South America, like lower light penetration through the water. So photosynthesis is going to be even lower, especially since it doesn't have nutrients coming up. But where you have rain here, we don't want rain here. Rain here is a disaster. It's a disaster because you have mountains here with a lot of deforestation happening. So there's not a lot of things that are anchoring any of the soil together, and we have a lot of mudslides and landslides, and it's a terrible thing. All right. That's about South America, but that's where the rain's going to go. In Australia, we're going to have fires. We're not going to have any food being produced here. So any of your crops are not going to be there. Tree. No tree. Okay. Lastly, this is a little bit of like a meteorological thing. Like it's kind of like combining the atmosphere and the ocean, which are very linked. But the ocean traps a lot of the heat from the atmosphere. And you're not getting a lot of atmospheric action over here in this area because those winds they're weak winds, either that or they're reversed. I'm going to go with the weakened ones. That's just my brain preference. That's going to cause the temperature of the water here to increase. And not even increase, but it's going to stay warmer than it normally is. Typically, that warm ocean temperature that heat can be transferred into the atmosphere. And that's not happening now because our winds aren't strong enough to even causing an effect. And then we can go into all the problems there, right? So we're going to have less crops, less profit for our farmers. We're going to have droughts, right? So it's going to cause less crops. It's warmer temperatures. We don't want to have warmer temperatures there for, like in the water, for our fish. Our fish are going to swim away. That's going to decrease biodiversity. We could have coral bleaching because the corals are not going to like that higher temperature. And we have a lot of corals there, right? The Great Barrier Reef. Less biodiversity in the water, less biodiversity at the coral reefs. Because we don't have like the normal weather patterns there, they're not going to have the same amount of like tropical cyclones. A tropical cyclone is a hurricane. A hurricane is a tropical cyclone. We call them cyclones in the Atlantic. We call them typhoons in like the Pacific. And the last thing, because we're not going to have, just something else you could talk about is there's going to be higher pressure. Higher pressure isn't a bad thing. Higher pressure means the weather's good. But that's just going to be the effect that's happening over there. So let's talk about fires as well. And all right, so the biggest thing here, we got to think about what are the winds doing. In El Nino, it's weak. We always go the trade route. We go from east to west. And we should be considering going from the west coast of South America, like by Peru, pushing over to Australia and Asia. And in El Nino, that's going to be a very weak wind. If you didn't, well, you do have this picture on the other page, but if you didn't, I would probably just do something like this. Here's my Australia. Here's South America. I literally would just sketch it out like that. And here's going to be the Pacific. And it's all about our winds. Never eat soggy waffles. We move this over. That's normal. And what's not normal is during El Nino, when we just have like these little tiny baby stupid winds. Or they reverse, but like I said, that's not my mental preference. All right, describe means what? Okay. Weaker trade winds. Keep warm water. Off the South American coast. Or you can say the trade winds reverse. That is fine. So they're going from west to east if you're going to talk about them reversing. Causing higher ocean temps in Australia. Because again, that heat is not being input into the atmosphere. We need the wind to be blowing over it for that to happen, and that's not happening. Okay, resulting in less rain or droughts. Again, we're in Australia. That's what this question's about. Which can increase forest fires. Forests, or we could say wildfires. Farmers have less crop harvest. We can also talk about farmers losing income. Less work for people. Okay. Kind of because of the ocean temperatures being high. I'll just pick off that for a second. Fish can go to deeper waters, so like away from where they're going to be able to be caught, because it's going to be colder there. Or you can say fish migrate to colder waters. You can also say that there's going to be less fish caught, like by fishermen. Corals may bleach, which means zooxanthellae leaves. Causing coral death. And if we have fish leaving and coral death, the reef biodiversity, the different species that are there, and the amount of them will decrease. Finally, there's going to be less typhoons or cyclones, say tropical storms. Due to the air pressure being higher. And I tell my students like to remember the difference in air pressure. If somebody was like, hey, how's the weather? And you give them like a thumbs up, high air pressure, like so thumbs pointing up, high, that would be good weather. But if you said, hey, how's the weather? And you go thumbs down, like the weather's bad, pointing down, like low air pressure. Low air pressure causes very volatile weather. That's where storms are from. Oh my gosh. All right, we did it. Holy cow. Good luck. Good luck on your test. And if you're going to ask for a paper 2, don't do it. Just kidding. I very well may. I know there's a few paper 2s on there. Yeah. All right. Good luck, everybody. Thanks for hanging out. If you stayed this long, I hope the best for you.